Compactness is a deep and powerful theorem. Suppose we have a set of formulas, possibly infinitely many. Is there a valuation that satisfies all of them at once? Compactness says yes, exactly when every finite subset is satisfiable. In other words, for propositional logic, the infinite whole is controlled by all of its finite pieces. The contrapositive form is often more useful. If the entire set of formulas is unsatisfiable, then some finite subset was already unsatisfiable. That means inconsistency cannot hide only at infinity. If the whole collection breaks, a finite fragment already contains enough information to witness the failure. The proof idea is constructive in spirit. Decide variables one by one. First choose a value for x1, then for x2, then for x3, and so on. At each stage, choose a value that keeps satisfiability possible for the remaining finite fragments. The infinite sequence of choices becomes a global valuation satisfying the whole set. Compactness gives a beautiful application to graph coloring. If every finite subgraph of an infinite graph can be colored with k colors, then the entire infinite graph can be colored with k colors. Encode the coloring problem using variables x sub v, I, meaning vertex v has color I. The finite subgraph condition gives finite satisfiability, and compactness gives a coloring of the whole infinite graph. The deeper meaning of compactness is that certain infinite logical problems are governed by finite evidence. The theorem does not necessarily give an efficient algorithm, but it gives a strong guarantee if a contradiction exists, a finite witness exists. This idea becomes essential when we move to first-order logic and Herbrand-style reasoning.